Hey guys, Andre Freeman here. All right, so we're looking at a problem here relating to finding the confidence interval for a population mean. And this is an example where we actually have the sample data, and we'll have to first compute the sample statistics. We'll use Desmos to do all of this, and then we'll make sure we interpret the results. So it says that a large city has an athletic facility that serves people of all ages. A researcher was interested in estimating the mean age of athletes who attend the facility. Over a 4-day period in the summer, the researcher randomly surveyed athletes and observed the following ages. So this sample, it appears, had 15 values. We'll confirm that when we put it into Desmos. So we have these 15 ages. It says create a 95% confidence interval to estimate the mean age of athletes who use the facility during this time period. And we'll complete these steps here as we do it. The first question asks, what are the sample statistics? So what we can do is, since this is a Word document, we can just copy these values into Desmos. So I'll Control C, and then in Desmos here, I open up a blank Desmos screen. I'm going to paste them, so Control V. And what we have to do in Desmos, anytime you're working with a data set, I'm going to just hit Enter first to kind of store it. And now when I go back here, I want to go to the beginning of the list. And actually, I'm going to just put a bracket here. Put a bracket at the end, a square bracket at the end. And since it's only 15 elements, it won't take that long to do this manually. A bracket here. And then I'll label this A. So A equals. So you see what we're doing is we're essentially storing the list A, labeled A, in Desmos. This is really nice because then what we can do is we can get a dot plot, we can get a histogram, we can compute the mean, the standard deviation, and various statistics on this data set. So let's look at the mean first. So that would be mean. So mean of A. And let's do standard deviation, STDEV of A. And since we have this, we might as well look at a quick dot plot. So let's do a quick dot plot of A as well. Now, what you need to do is use these tools here. So this magnifying glass zoom fit allows us to have a nice view of this dot plot. And we can see that most of the values are around 20, but then there are some values over here that appears to be outliers. We could also do a box and whisker plot or a box plot, but this is certainly sufficient for our problem here related to inference. So these sample statistics, the sample size, the sample mean, and the sample standard deviation are really the key to moving forward. So let's begin to write this down. So the sample statistics here for part A, we have a sample size of 15, a sample mean of, oh, I already forgot it, of 27.2, and a sample standard deviation, S, of, let's round this to 2 decimal places, of 12.62. The next step in the process is to verify whether the normality criteria are met. So when estimating a population mean using a sample mean and a random sample, we're looking for 2 criteria. We want the sample size to be at least 30, or we want the population to be normally distributed. So there should be an assumption that the population is normally distributed. Now, I don't think I put that in this problem, but to move forward, let's just make the assumption that the ages of the athletes who attend this facility, let's just assume that the ages of the folks who attend this facility are normally distributed. Now, looking at the sample kind of was a little bit skewed, but that's okay. We'll just make this assumption so we can move forward. But we really need this to be the case. If the actual ages themselves are of the population of athletes who attend this facility are not normally distributed, then it's very unlikely that the interval that we establish will have a lot of validity. So what we're going to do here is we're going to just make this assumption, and then we'll move forward with our inference process. The margin of error is important. This is going to be based on the confidence level. So this is where you have to be really careful about what you're doing. We're going to use a t-distribution to compute the margin of error, a t-distribution critical value, because of the fact that we have a sample standard deviation, right? We know, or we have S, but we don't have sigma. So since we don't have the population standard deviation and we only have the sample standard deviation, we have to use a t-distribution. So the formula for the margin of error is going to be the t-distribution critical value times the sample standard deviation over the square root of the sample size. Now, let's focus on how we get this t-distribution critical value. So there's two ways of doing this. We can certainly use a table. And if we use the t-distribution critical value table, which you guys have access to, we can simply look at the confidence level and the degrees of freedom. Let me go back a step. The sample size in this problem is 15. So that means we have 14 degrees of freedom. When we have a single sample inference problem, the degrees of freedom is going to be the sample size minus 1. So we have 14 degrees of freedom. And we have a confidence level up here, I'll just write it here, of 95%. So 0.95 or 95%. So going to the table, 95% confidence, 14 degrees of freedom, we get a critical value here of 2.145. 2.145 is the critical value for this margin of error calculation. So that's important that you correctly identify the critical value, and we can use tables to do that. So we can conclude here that T sub C is 2.145. Excuse me. We can also real quickly use technology to do this. And what we're basically saying is if we have a t-distribution with 14 degrees of freedom. So this is the t-distribution that has 14 degrees of freedom. We're saying we're looking for, now this is a standardized distribution, so the mean is 0. We're basically looking for two t-scores, a negative one here and a positive one here, such that the middle area between these two critical values, really between these two t-scores, is 0.95. If that's the case, then the area in this tail would be 2.5%, 0.025. And the area in this tail would also be 0.025. So the sum of the areas in the tail, the middle area of 95%, and the area in this tail, the sum of those areas should be 100%. 100% of the values are contained within the distribution. So what we'll do in Desmos is we can, now again, you don't have to do any of this because we already found the value from the table, but just in case you wanted to see how technology could be used, in Desmos, I'll show you real quickly, we're going to use the inverse CDF command, and we're going to use this command to find the negative t-score. We're going to use it to find this value, this negative one. And then from there, we can reason that the positive value would be the opposite, and then the critical value would be just a positive number. So real quickly in Desmos, we'll do inverse CDF, and I'm going to enter in the t-distribution. So t-distribution that has 14 degrees of freedom. And the next parameter in this command is the area to the left. So if you go back up to the diagram, see how the area to the left of this negative t-score is 0.025? We're looking to find what is the negative t-score in the t-distribution with 14 degrees of freedom that has an area of 0.025 to its left. So we're going to enter in 0.025 here. And the output of this command is the actual t-score. So you see we're getting negative 2.1447. If we approximate, it'd be negative 2.145. So we're basically getting in Desmos that this value here, that value there, is negative 2.145. And again, using the symmetry, that means that this would be positive 2.145, the t-score that has 2.5% of the values to its right. So therefore, the critical value for 95% confidence would be the positive number 2.145. And essentially what we're saying is that 95% of values in the t-distribution with 14 degrees of freedom are within 2.145 standard deviations from the center. So that was a long explanation for something that, again, is not necessary. This table that I showed you here is really helpful for finding t-distribution critical values for different confidence levels. And there's also other technology you can use to do this. All right, so let's wrap this up. So the margin of error for 95% confidence is going to be 2.145 times S. The sample standard deviation is 12.62 divided by the square root of the sample size, which is 15. So we can do this in Desmos as well. Okay, so we have 2.145 times, and the numbers are right here, 12.62 divided by square root SQRT. It converts it to the square root sign of 15. So we're getting a margin of error of 6.99 if we round to 2 decimal places, 6.99. The margin of error basically is an estimate of the distance that a certain percentage of sample means are from the population mean. So here we would interpret this to say that 95% of sample means from random samples of size 15 are within this distance from the population mean. Now we don't know the population mean, so we're going to now apply this margin of error to the sample mean that we have. And now we're going on to part D, where the confidence interval is going to be the sample mean plus or minus the margin of error. So that's going to lead us to the sample mean was, let's go back up to the top, 27.2 was the average of the ages of the athletes in the sample. 27.2 plus or minus the margin of error is 6.99. So this is one way of writing it. Then we can also write it as an interval. So it'd be the sample mean minus 6.99, sample mean plus 6.99. And then we can wrap this up. So this becomes, go back to Desmos to finish this. So again, I really think this is a handy calculator to use. And once you get used to using it, I think if you choose to use it, you'll find that it's pretty easy to use. So the lower limit of the interval is 20.21, and the upper limit of the interval is 34.19. So we have 20.21, and the other value was 34.19. Okay, so I hope this helps. We can conclude that we are, and in terms of the last step, I'll just say it verbally, we are 95% confident that the mean age of all athletes who attend the facility during this time frame is between 20.21 years and 34.19 years. All right, guys, keep working hard.